So, and now if we want to define for any generic x and y, then we need to take care of the intervals as we did for the one variable. So you will have to start by being less than 0 and less than 1, being out there, not touching anything, then touching this first one, then touching that, then including that, then including this, then one after another, including all of them all the way to the end. So you have several intervals depending on where x is, whether x is between 0 and 1 or between 1 and 2 or after 2. You will split for each of the random variables and pick a combination of two intervals from the number of intervals that you get. That's not really very important at this point, so I'm not going to spend a lot of time on that. The principle from it was just to show you that here's how it works on one simple example. Now, if that was a continuous random variable, then it's going to be defined x1, x2 of little x1 with x2 is equal to the probability x1 less than or equal to x1. Yeah, let me finish right now. And this would be an integral. Say negative infinity x1. So you have to take that joint distribution and integrate from negative infinity to x2 and integrate from negative infinity to x1 together, get the joint distribution. So expected value it defines same as before. You need the condition that the expected value of the absolute value is finite, and then you will have to integrate negative infinity to infinity the function g of x1, x2 times the joint distribution. Or for a discrete random variable, the sum over all x1, x2 of g of x1, x2 and for x1, x2 for discrete random variables. An example of this would be the famous guy we talked about last time, the moment generating function. It exists for one variable, it exists for vectors as well. How do we define that? That's m x1, x2 of t1, t2, because now you are dealing with a vector. There are now two values of t that are going to be in the definition. It's expected value of e to the power t1 x1 plus t2 x2. So that's how you find the moment generating function of the vector x1 x2. From this, you can find the moment generating function of x1 and x2 separate. From this, we have x1 of t1. If you're just looking for the moment generating function of x1, it will be same as plugging in here t2 equals 0. So if you already have the joint moment generating function, you don't need to write a formula and compute again. You just plug in 0 to get the moment generating function of x1. And get the moment generating function of x2 the same way by setting t1 equals 0. So when you do this, you get the moment generating functions of x1 and x2 separately. Let's work out an example with these expectations and the moment generating function. So we have the joint distribution f x1, x2 equals e to negative x2 if 0 is less than or equal to x1 less than or equal to x2 finite, 0 elsewhere. So that's the joint PDF of x1, x2. And our job is to find the moment generating function of the variable x1, x2, find the moment generating function of x1 and x2 separately, and perhaps find the marginal distributions, which are the things that we put on the board last time without working out some examples. So we do that now on this. One, m x1, x2, t1, t2, x1 of t, and x2 of t. Find the marginal CDF of x1 and x2. So find the marginal cumulative distribution functions of x1 and x2. All that from this. Okay. So how do we answer this? So by the way, quick question. So what do you guys prefer? Explaining theoretical things or spending more time solving problems? No, we like to vote in this country. And every time I propose to vote in this country, like 1, 2 people say something, and the rest is just like, whatever. So she'll be fine anyways. Okay, so I mean it's like a draw. One person says problems, one person says theory, so I'll somehow do it. Now, so how do we find the moment generated function here? It says that m x1, x2 of t1, t2 is equal to the expected value of e to the t1 x1 plus t2 x2. That's the definition. In order to write down the formula for this, first let's say this is by definition integral. Is that negative infinity to infinity, negative infinity to infinity, right? And the function is e to the t1 x1 plus t2 x2. Then what? F x1 x2, right? D x1 dx2, or we could put dx2 dx1 first, and then start thinking how to continue. Yeah, let me go dx2 dx1. Quite better. Why is that? It's because of what I have here, this inequality. Now, in order to put in fx1, this is the most difficult problem we have here. Right here is how to write that fx1, x2 inside here, knowing that this is the boundary and we have this condition. Does that make sense? So we can't just come here and write e to negative x2 and start computing. That would be wrong. Because to plug in e to negative x2, you need to know that the boundary of integration need to respect the fact that out of this range, f is 0. That's a very common mistake to forget that. So, and in order to know what to do, we perhaps need to sketch this to see what it looks like. So if I try to sketch this, and I can start here because it says that all the x1 and x2 are positive, so I'm not thinking there's anything in a negative direction. And I have an inequality here. X1 is always less than x2, right? What's that? I don't know what you're saying.
Can you move the paper up?
Move it up.
So that we can see what you're.
Oh, where I'm drawing, but I need you to see what I'm showing here as well. If I put it up, that goes out. So what I need you to see is here, not yet here. I'm interested in you understanding here. X1 is less than X2. Whenever the PDF is equal to e to negative X2, X1 is less than X2. So we need into this range to remove everything where X2 is less than X1 and figure out now how to put the boundary of integration here. That's what is going to help us. Okay. So here, now if we go into this graph, And for x1 less than x2, the equality gives this thing here. Let's start here with 1 and 1. And this is why I was telling you last time, be careful when you're sketching. Make sure perhaps the properties are seen of the variable that you're drawing. When is it 0? When is it equal to 1? Those things are important when you're using the distributions. So here, x1 equal x2 would go along that line. That's the diagonal. The main diagonal will be where it stops. And now you need to choose. This here is x1 on this side, and that is x2. And you need to choose on what side of this line is the region of interest. How do we choose that? How do I know which of the two portions satisfies the inequality that x1 is less than x2?
Would be the upper portion where the x2 would be greater than the x1.
That's correct, but how do I know that? If it was a different problem with a different inequality, something more complex, how do I know? Huh? Pick up a point, usually that's what you do. Pick any point, either here or here, and check that inequality. If it holds for one point, it's going to hold for any other point in that region. Why is that? Because the equality is at what x1 equal x2. So everything here is going to have the same direction of the inequality, and everything up there is going to have the same direction of the inequality. And that would work even if it's not a line. That's the reason why you need to know exactly why you're doing that. So that any other problem, just know, okay, I'm going to pick that and plug in. If that satisfies, then this is the region that I'm interested in. So here, if we pick a point here, that could be like 1, 2 here. If I pick this point, 1 and 2 for x2, then you check, is x1 less than x2? Yes, so it's here. So 1 is less than 2. So that's the region where the density is not equal to 0. So everywhere here, the density of that random variable is 0. And so if I want to compute this integral, every time I fix a value of x1, every time I fix the value of x1, so please follow me now. And that would work in any other problem. If I fix a value of x1, and I want to integrate with respect to x2, that's how we do in Calc4. So when you fix x1, you integrate first with respect to x2. But then you account only for the values of x2 that fall within this region for that value of x1. So, what? So I'm going to draw a line parallel to the x2 axis and cross the region. And I'm going to take only the values of x2 that fall in the region. Because as I am drawing this thing up here, these values of x2 are not yet in the region of integration. Till I reach this point, that's where I start getting into that region and continue going up. Where does it stop there? As I'm going up, does it stop being in the region? No, so it goes up to infinity. Where does it stop here? For the fixed value of x1, which is x1, where does this thing stop? On this line, what is x2? Huh? What's the value of x2 then? x1. So right here, for that fixed value of x1, x2, where you starting your integration is x1. So this integral is going to go from x1 to infinity. And then after integrating with respect to that x2, there will be no more x2 inside that integral. I will be left with x1. And now where is the range where I can fix my x1? It starts here, it ends where? Infinity. So it's 0 to infinity. So that's where I can fix my value of x1. So that's what goes here, 0 to infinity. That's it. And after doing that, now you know you can put e to the t1 x1 plus t2 x2 times e to negative x2 dx2 dx1. Questions about this? Again, from one problem to another, what changes is that range that you're working for. And you need to know this procedure always works because the only thing that will change from one problem to another is where you're crossing. And remember here, I was asking you where it stops because in some problems it can stop. If that range also ends up there, then you will have to stop where that region ends. So now we compute the integral. How does it go? It's what we call iterated integral. So you compute this one first, then you plug it back in and you compute the second one. So integral from x1 to infinity of e to the t1 x1 plus t2 x2 and then minus x2 x2. What is this equal to? How do we integrate this? How? Okay, take that out. Okay. And I can actually do something better. I can put here negative x2 times 1 x2. And now you can integrate this. So how do we end this integration? And who can explain why I actually pull out the negative to put here? Huh? Because e to the minus infinity is 0. So I'm expecting you to see that there should be a condition here that this number here is positive. 1 minus t2 is positive. So you get that, which means t2 is less than 1. which is good because actually we are more interested into the zeros, right? The neighborhood of zero. So this is a good condition. And now, if I have this condition, therefore I know that when I plug in infinity, I get zero. Otherwise, it doesn't work. And then I plug in x1. When I plug in x1 here, with the minus that was here, it becomes plus. So you get e to the t1 x1 times e to the negative x1 times 1 minus t2, all that over 1 minus t2. So that's the first integral. Strange. Camera has disappeared. So we are back. So you had for a few seconds an old picture of my son. Sorry about that. It's not Bivariate. It's not statistics. It's one statistic of my life. Now we have this integral, and next what do? We take this and plug into the integral dx1 to continue. Let me copy that here. So the next step is x1, x2 of t1, t2 equals integral 0 to infinity of e to the t1 x1 times e to the negative x1 times 1 minus t2 dx1 over 1 minus t2. And then next what we do is we use the same rules to compute this other integral. So that's equal. We can take out the 1 over 1 minus t2 and now integrate 0 to infinity. We can use the same principle, put a negative sign out there, negative x1, and then we are left with 1 minus t2 minus t1. Oh, that's not t squared, but t2, okay? dx1. Everybody agrees with that? Okay. And then to finish integrating, we also have the condition, same as before, that this number here is positive. So 1 minus t2 minus t1 is positive, so that the integral converges. And that's going to give you t1 plus t2 is less than 1. And all the first condition was t2 is less than 1. And these two conditions are compatible, which is fine. It's T2, not T squared. I don't know why I keep trying to put that up. And so when you integrate this, you get 1 over 1 minus T2, and then e to negative x1 times 1 minus T1 minus T2 over negative 1 minus T1 minus T2 from 0. Again, with the condition that T1 plus T2 is less than 1, when you plug it infinity, you get 0. Then minus with this minus cancels. So your answer gives you, and then exponential 0 is 1. So you get 1 over 1 minus T2 times 1 minus T1 minus T2. So this is the moment generating function of x1, x2. Now, jumping ahead to some of the things that we will see, you can see that in this moment generating function here, you cannot separate T1 and T2, right? They are combined in this 1 minus T1 minus T2 times another function of T2. So there's no way you can write this function as a product of T1 times a function of T2. No way, just. And the reason being that the two random variables that we have in this case are not independent. Okay. The moment generating function can only be written as a product of the moment generating functions of the components if you have that fact that they are independent. If you start by independent random variables, then you are going to end up with random variables with moment generating function equal to the product of the two. Now the second part of the question was find the marginal moment generating functions. And so the formula said to get this, it's easy. You just need to plug in T2 equals 0. Equal m x1, x2 of T1, 0, which is 1 over 1 minus 0 times 1 minus T1 minus 0. So that is 1 over 1 minus T1. So this is the moment generating function of x. To find that of T2, use that 1 minus T2 times 1 minus 0 minus T2 equals 1 over 1 minus T2 squared. Now you can replace T1 and T2 by T. The third part of the question was find marginal CDF x1, x2, what's plural? There are two ways to actually answer this. To find the marginal CDFs, knowing that here you already have the marginal moment generating function. If you know a way of going from the marginal moment generating function to the distribution, you can apply that to find the answer here. Or you can go back to the definitions that I gave you last time to find marginal PDF first, then use the marginal PDF to find the marginal CDF by taking the input. Okay? And that's the part that I'm going through to apply what we did last time. So for X1, the marginal TF is fx1 of x1 equals integral from negative infinity to infinity f x1 x2 dx2. This is how you find the marginal PDF of one of the two random variables by integrating the joint PDF with respect to one of the variables. And the same issue that we just had comes back. To put in the formula of f, we need to know what's the range of integration. And knowing that x1 here is fixed, we go back to that. Our graph. When x1 is fixed, what is the range of y? From x1 to infinity, right? That same graph comes back here. So it is important to have the correct graph. Otherwise, all your questions are down. So when I am looking for the marginal distribution of x1, x1 is fixed because it's inside the function and I'm integrating over the entire range of y. But I know that in that range, my integral has to start at x1 because before x1, x2 has to be larger than x1. And then it's e to negative x2 x2. And now you can integrate this. And it's e to negative x2 over minus 1 from x1 to infinity. And good news, when you plug it in infinity, this is 0. And when you plug in x1 with the minus that is here, you get e to negative x1. Which implies that is with x1 positive, right? Because that's the range of x1 that we have, x1 positive. So what happens is that this density is therefore equal to e to negative x1 for x1 positive and 0 for x1 less than 0. Because there's no value of x1 below 0. This distribution actually called the exponential distribution with parameter 1. So x1 follows the exponential distribution with parameter 1. And now from this, we can find the CDF. x1 of x1 is integral from negative infinity to x1 of f x1 of t dt. And in this, when x1 is less than 0, it is 0. When x1 is larger than 0, you integrate this thing, you get 1 minus e to negative x1. It doesn't matter actually where you put the or equal, as I said last time. Right? So this is the marginal CDF of x1. That's how you use the joint distribution to find the distributions of the random variables, the marginal distributions. Now we can do the same thing for x2. Ready? Everybody okay? Now you tell me, how do we do for x2? What would be the range of integration for x2? So for x2, marginal PDF is integral from negative infinity to infinity of x1, x2, dx1. Now we integrate dx1 to get the marginal distribution of x2. So you tell me, what would be the range here? How do we integrate? From what to what? 0 to 0 to x1. When you're integrating dx1 and you're finding a function of x2, you can't end with x1. Because if the boundary of your integration is x1, that means x1 is going to be in the function at the end. Right? But you need to have a function of x2. Now looking at this same graph that I gave you earlier, how would we integrate dx2? Oh, sorry, dx1. To integrate dx1, where do we fix the random variable? Where do we fix the value? We start here fixing x1 because we were integrating dx2. Now that we are integrating dx1, what are we fixing? Fixing a value of x2. Where are the values of x2? Up here. So if I'm fixing a value of x2 here, what are the values of x1 that are in the range? That's the question. So you 0 to, you're integrating dx1, so x2. So that's the game you need to play all the time. Know that when you go integrating with the other, you go to that line, you fix, you put that number there, and you go across your range to make sure you see the numbers that you put as boundary. And when I take x2 fix here, my range of x1 starts here 0, and I continue throughout the region that I exit. When I'm exiting, what's the value of x1? It can be x1 because you're looking for the value of x1, right? So it is x2 because this line says x1 equal x2 right there. That's it. So here it's going to be 0 to x2. And then after that, you put that function in now, e to negative x2, dx1, right? That's right there. And now this is so nice because x2 is no part of this, and the integral is just x2. So that is x2 e to negative x2. That's the PDF. With the condition, what's the condition on x2? What's the range of x2 once it's fixed? Where do you fix x2? Huh? 0 to? Is there a boundary there? 0 to infinity. That's where you're fixing x2. x2 is anything from 0 to infinity. You fixed it here, but you're choosing this thing that you're fixing from what? From 0 to infinity. That's why the range at the end here is x2 larger than 0 just. Because you're fixing it from 0 to infinity. Now, what was your question about the integral? What was that again? Say it.
I just realized what you did.
It'll be good for us if we realize what you realized.
I was thinking, like, by x1, by x1 is, I realized that you
Log
replaced x1 with x2.
Yeah, you integrate, you get x1 equal to, you're absolutely right, and then you plug in the values of the boundary, which are x2 and 0. The bottom is 0, and the top is x2. That's why you get x2. Good. It's good to say. All right. Any other questions on this? No? So that's how we found the marginal distribution of x2. That's little f, okay? That's not capital F yet. Who said that? I wrote marginal PDF, okay? So that's just the marginal PDF, and you still got to use it to find the marginal CDF, which will be the integral. Okay? So how do we call this kind of function? This kind of PDF. What kind of distribution is it? Huh? Yes, it's the marginal distribution of x2, but it's a specific distribution in statistics. It has a name. Like the previous one I told you is the exponential distribution. And by the end of this class, I mean, when we finish this course, you need to memorize those distributions. So the exponential is e to the negative x over lambda. Now, this one, how do we call it? It's a gamma distribution. Gamma. Because it has two parameters. One that goes inside here, and the other one that goes as power of x outside. When the time comes, you learn about it. I'm just getting ahead to tell you what it is. And the two distributions are related, the exponential and the gamma. We'll get to it. Now, the CDF, the marginal CDF of x2 would be fx2 of fluid x2 equals integral negative infinity to x2 of fluid f x2 of x of t. So again, here, same thing as you want to integrate. You remember the range of x2 before 0, capital F is 0, and it starting at 0, you compute the integral. So if x2 is larger than 0, fx2 of little x2 is integral from 0 to x2 of t e to negative t dt. Reason why you always change the variable inside is to make sure you don't get confused by writing x2 here and then x2 as boundary of integration. Then after integrating, you forget to plug in the upper and lower bounds. So how do we integrate this one? By parts, right? You have a question, ask me, please. When you're asking your classmate, you're making two people be behind. So we integrate that by parts. Okay, so it's going to be t e to negative t over minus 1, 0 to x2 minus involve 0 to x2, and then derivative times e to negative t over minus 1 dt. So if you remember integration by parts, not, you know it's integral of u dv equals uv minus integral of v du. That's what we call integrating by part. In this case, u is t, dv is e to negative t dt. So u being t, du becomes just dt. And v is the function that has derivative e to negative t, which is e to negative t over minus 1. And then the parts give this. And so you can plug in the numbers. When you plug in t equals 0, t equals 0, you get 0. When you plug in s2, minus x2, e to negative x2. And then you integrate here what you get. Minus, and then e to the x2 minus 1. So in the end, you get 1 minus x2 e to the x2 minus e to the x2. That is when x2 is positive, 0 x2 is any questions? So this is how you would use a joint distribution to find the marginal CDFs of x1 and x2. And the next thing in this is how to find the conditional distribution, which is like what we were doing at the beginning, but for discrete random variables. Here, if we have a continuous random variable, how do we find the conditional distribution? So here, conditional for PDF and CDF. How do we find them? So f x1 given x2, the notation is this, of little x1 given little x2 means if the random variable x2 is equal to x2, what is the distribution of x1? Which means, and that gives you a meaning of what I was doing on this graph. On this graph, when I tell you that I fix a value of x1 and then I go through the range, that means if I fix the value of x1 here, what is the distribution of x2 on this arrow that goes up? And if I fix the value of x2 here, what's the distribution of x1 on this piece? That's what the conditional probabilities are about. Okay? And that is important when you're modeling something where you have the choice of fixing a level of one variable. You can fix a level of one variable, not change it, and have things vary among other variables, and then you use that to have inference on what is happening. And so here the definition is simple. It is the joint distribution of x1, x2 divided by the PDF marginal x2 of x2. X2 given x1 of little x2 given x1 is the joint distribution over the distribution of x1. In this example, fx1 given x2 of x1 given x2 equals, what was the joint distribution? E to negative x2 divided by, what's the PDF of x2? PDF of x2 is, that's the PDF of x2 out there. We got it. x2 e to negative x2, right? So that's it there. And so that's what we are taking down here. That's x2 e to negative x2. And these things cancel. That's 1 over x2. Okay, notice that this is the distribution of x1 given x2, right? So x2 is fixed. For every fixed value of x2, the chance of having x1 is a constant. Do you see that? It doesn't depend on x1, which means what? That x1 is uniform, conditional on x2. Notice that this thing is under one condition. One condition. What is the condition here? That 0 is less than x1, less than x2. Because in the definition, x1 is always less than x2. So whenever you condition on x2, you know you can no more get a value of x1 that is larger than that x2. That makes sense? Because in the definition, in the original definition, you know that x1 is always less than x2. And that is why this is actually, yes, this is the uniform distribution. So this is uniform 0x2. The distribution that is uniform on 0x2 assigns value 1 over x2 to everything. Remember, I think it was first or our second lecture where I defined the uniform distribution on AB, on the interval AB. So if you read that, you will see that this is exactly what you obtain for the interval from 0 to x2. And that's the conditional distribution of x1. Now, what would be the conditional distribution of x2 given x1? That will be again e2 negative x2, the first, divided by, and what's the distribution of x1? What's the PDF of x1 we found? PDF. E2 with x1. It's very important. E to negative x1, because if you put negative x2 there, they cancel, it becomes 1, and it's wrong. So it's e to negative x2 over e to negative x1. And with the condition that what? That the x2 that you're dealing with is larger than that given x1, right? That's the thing. In this case, it looks like what we call the truncated exponential distribution. So you took a random variable that was exponential, and then you caught it at x1, and you're just looking at the tail. Right? So in this case, that's what the distribution is equal to. Now one could ask you the question, what is, to get the CDF, of course, we integrate this. The conditional CDF, just integrate this, integrate that, you get what it is. What I'm interested in is the conditional expectation. Which you obtain using the conditional distributions the same way you use the definition of the expected values. So here, how do we do this? We say conditional expected value of x1 given x2 equals, you are going to integrate x1 times the conditional distribution of x1 given x2, x1 given x2, and d would be d what here? What's the d that you have here? x1. It's your integrate. It's the expected value of x1. x2 is fixed. And so that's what you would do in this case. And for this one, you know that x2 is between, x1 is between 0 and x2. And so that's going to be x1 times 1 over x2 d x1. So when you integrate that, you get x1 squared over 2, plug in that, you get x2 squared over 2x2. So the answer is x2 over 2. And this is understandable because here I explained to you that this is the uniform distribution on 0, 1, right? What's the expected value of the uniform distribution on an interval? It's the middle of the interval. The middle of the interval from 0 to x over 2 is at x over 2. Okay. Whenever you fix x2, the expected value of x1 in this case is half of x2. You can do the same thing for the other. I think we ran out of time. I see people looking at me say, when is he going to stop? So maybe it's better we stop now. Thank you very much. If you have any questions, feel free to ask. If not, feel free to go. Hey, Taylor, how are you doing?
Not great.
Yeah. I wish you feel better.